Wait, is it the 21st or the 22nd?
21st, I think.
Oh, then I'm all screwed up. Okay, anyway, let's talk. Thank you, sir. That's okay. And I just recorded that. It's going on YouTube. Okay, let's talk about accuracy versus precision. I heard some of you looking this up and reading the definition of one another. Accuracy is how close you are to right. Accuracy is the closest of measurements to the true value. Correct answer. What the reference says. What the chemical engineer's handbook says about the density of nickel. What authoritative figures say about this is the true value. If you're close to that, you're being accurate. Now, precision is a whole different thing, because precision is how good you are at making the measurement, and it's how good the instrument is. So I can get dead lucky with something, and I can be doing a really sloppy job and get really lucky and get the right answer. I could throw a dart at a wall with answers written on it, and maybe get the right answer. But if I am measuring in a way that is careful and precise, and I am using an instrument which is well made and precise, I should be able to measure the same thing 10 times and get almost the exact same answer 10 times. Okay? The standard sort of illustration we give for this, it's kind of an archery example. And I have often joked that, well, I always wanted to, when I was a kid, it wasn't Katniss, it was Robin Hood, and I just wanted a bow and arrow more than anything in the world, so I made them out of sticks and pieces of, baler twine. They were really, really ineffective. Yeah, as you can imagine. But I probably wouldn't have been any good had I gotten a real bow and arrow finally. What we look at with accuracy. So if that's our bullseye. If we are landing our shots all in that bullseye, in that target, we are doing a good job with accuracy. We're hitting the target. And I'll move this up to accuracy. That's accurate. Now, if I have a hard time hitting the target, but I can split my arrow, I can cluster all my shots in one area, that's precise. I'm not getting the true value. I'm not getting the target. I'm not hitting the center. But I'm able to hit the same spot repeatedly. Now, the best of all possible worlds, so this is precise. The best of all possible worlds, of course, is if you can be both accurate and precise. You make the measurement repeatedly the same way, you get the same values again and again, and those values are right. They're near the true value. That's awesome. Well, what if you do a job that's more like this? Boop, boop, boop. It's a little hard to see. Let me give you a bigger view of that. So I get a shot there, and a shot there. Maybe I even get a shot there. If I average those shots, it's funny to think about averaging a physical object. We think about averaging numbers. If I average those 4 shots, hey, pretty good. None of them hit the target. They average out to the true value. They average out to about the middle. I could call it accurate. I can average my shots and say, yeah, I'm right around the bullseye. But they're not precise. They're off in all directions. So the question then becomes, when we have a set of measurements that are precise, that are accurate, that average to a true value, or something that we think is close to the true value, we don't really know which one of them is, if you're not doing precise measurement, we never know if the numbers are going to average to that true value. So precision is really critical. And precision comes from both quality of your instrument and your own skill in using it. You guys in the lab that I asked you to get out all used pretty similar instruments. You had crappy rulers, basically. You had student-grade chemical glassware. These are not high precision, like crazy expensive instruments. But you can still do the very best job you can of making those measurements. We're always looking for error when we're making measurements. We're looking for ways to eliminate error. So I had one group that noticed that the top of the graduated cylinder is flared. Maybe a few groups noticed it. I know one group talked about it. And they thought, well, we can eliminate the error on that flare by measuring across the bottom. It's a good idea. It's a way to eliminate error. I had a few groups who realized immediately that there's a little bit of dead space at the bottom of the ruler. And that the only way to eliminate that was by measuring on the outside, not the inside. Because again, it's a source of error. So your level of precision comes down to two things. I mean, the quality of your instruments, but you can still do you can do a better job or a worse job with a crappy instrument. And I have heard it said, what is it? It's a poor craftsman who blames the tool. And there's some truth to that, though. There are also better and lesser instruments. A highly precise, well-calibrated micrometer. Has anybody here used a micrometer? Do you know what a micrometer is? Hold on. That's a micrometer. So this is it's a digital instrument. We also have one that's non-digital. It's an analog micrometer. And you can measure the outside of an object with that flat edge, and it will give you a very exact reading. You can read in millimeters or inches. You can toggle back and forth. You can also measure the inside of something with those. Do you think that that would have given you a better measurement of the inside of your graduated cylinder? Yeah. Oh, heck yeah. Than, a crappy broken red dime store ruler? Yeah. This is a much more precise instrument than what you were using. So, precision versus accuracy. How many of you feel like you had relatively high precision? How would you know? How would you know that? Talk about it amongst your lab group. I like that you're sitting in lab groups. And I'm sorry, it's a caliper. It's not a micrometer. Caliper. Okay, how do you know? How do you know? I'll tell you how you know. Oh, who said error? You know by figuring out your error. So if you look at all your reading, now error really, it tells you how accurate you are. But if you did multiple measurements and they all come up with about the same amount of error, you're also doing precise measurement. So your accuracy is determined by your percent error. But looking at a series of measurements that you made, how many people measured their cylinder more than once? I know a couple groups did. If those measurements come out very close to one another, you're doing a very precise job of measuring. I know I had one group who they had like crazy numbers, and I went over and helped them measure, and their first measurement was like 3.1, and I said, I'm seeing 2.8, and then they measured it again, and they got like 2.9, and then the other person measured it, Those aren't all that precise. They're varying pretty widely. So if you have done precise measurements, all of your measurements should have about the same amount of error. If you've done very accurate measurements, your error numbers should be very, very low. You've already calculated error, we just didn't call it that. What did we call it? What does this look like? What formula you've used? Does it remind you of anything? Percent loss. I heard that. Yeah, it looks an awful lot like percent loss. Well, what is loss but an error in recovery? That's what loss is. It's an error in how much stuff you were able to recover. So when we do percent loss, or percent error rather, We take, so your percent error, well, the accepted value. Okay. Where is your accepted value coming from? Typically an expert or an expert source. Chemical Engineer's Handbook, your textbook, the periodic table. We don't use that a whole lot for things that we're going to calculate error on. But your accepted value is some authority source of what something should have as a mass, as a volume, as a density, minus the measured, or we can say experimental, value. Divided by the accepted value. So this is very much like that whole percent loss thing. Okay. To make this a fraction, because you're going to get a decimal number here, you're going to multiply by 100. And that equals your percent error. Boy, I'm not writing well this morning. That equals your percent error. So accepted value minus measured or experimental divided by accepted is going to give, times 100 is going to give you your percent error. Can you have a positive or a negative percent error? Yeah. Okay, Matt. When would you have, last time he nods his head, I'm sorry. I wasn't nodding my head, I was just yawning. When would we have a positive? Yeah. Yeah. So if your measurements are lower than the accepted value, if the accepted value is greater, then you're going to have a positive percent error. Okay. In terms, if we're thinking about error in terms of loss, that means you didn't recover all your material, right? When would we have a negative percent error? Can you have a negative percent error? Oh yeah. When would we have that, Kendra? Yeah. When this number is a little bit larger than the accepted value, you're going to see a negative percent error. Did anybody have a density value for nickel that was higher than what the reference source, the engineering toolbox, said it was? I think they give the density of nickel as 8.9. Is that correct? So which groups had a higher experimental value for the density of nickel? Didn't somebody have 12 something? That was you. Okay, that's fine. That's fine. We're looking at pretty imprecise tools, but in this lab, this is the one lab of the year where I'm not rooting for you to make mistakes, but I want you to have some errors so that you can think about where those errors come from. It's definitely one where we learn a whole lot more by having numbers that are a little bit wacky and going, oh, well, where's the source of our error, than by doing everything perfectly the first time. Okay, so that's percent error. Now, let's talk about significant figures. Raise your hand, no T-Rexing, if you have ever heard of Sigfigs. One of you. Okay, where'd you hear it?
I just heard it.
Okay, you just heard. You didn't have it in, because we don't usually get any of this in physical science. It's kind of not something that we talk about until now. There comes a time in everybody's life where someone has to talk to them about Sigfigs. This is it, kids. It's the big talk. So, Sigfigs. Sigfigs are just a way. I should have another slide in there. Sigfigs are a way of keeping track of how precise the instrument we used was. That's all they are. And we get Sigfigs from the instruments that we're using to make measurements. If you're the one making the measurements, you determine how many Sigfigs there are. We're going to talk about what Sigfigs are and stuff in a second. But I'm going to hand each group a stick. Carefully and lovingly taped. Never mind the edges, I was in a hurry. This is kind of like that crazy guy in the blackout suit at the game. It really creeped my daughter out. Kind of creeped me out too, honestly. It's okay. Mama, why does that man look so strange? It's okay, honey. Just keep walking. I didn't know who it was. I didn't know it was you. Just some creepy looking guy with no face. Ugh. Okay, so you have a stick in front of you. Yeah, thanks, Moser. Captain of the obvious there. I'm going to tell you that that stick is exactly 1 meter long. No more, no less. Okay, no cheating and like poking through the tape. Are there any markings on that stick? Not now. I obscured them with painter's tape this morning. Just 'cause. Okay. There are no markings on that stick. Can you measure the widest part of one of your desks using that stick? Okay, Kendra, how long is your desk? Now, remember, because this is a trick question. This is totally a trick question. I know, nothing to make you nervous, like telling you it's a trick question. Remember that you can only have as many digits in your answer as the last marking on your instrument. We talked about this a little bit with your balances, with the centigram balances. What's the last marking on that instrument? I can pick on somebody else before I let Kendra answer the trick question, the dangerous territory. You can talk about it amongst your table. What's the last marking on that instrument? This is also a trick question. But there's an answer. There's a real answer. What's the last marking on that instrument? What is it? Go ahead. You look like you have an answer, Andrew. Don't lift the tape!
There's nothing physically.
Okay, there are no markings. So the last marking is basically 1 meter because the stick is 1 meter long. So with any kind of certainty, what can you say about your desk and its width? Remember, you can only go 1 digit beyond the last marking. And the last marking is 1. I'll make that in black so it shows up. 1 meter. So how wide could we say that desk is with any kind of certainty? Okay. So it's definitely a little bit less than 1 at its widest point. Would you all agree? Okay. Could we say it's 1.95? 1.7? 0.9? We can probably estimate that. So here's the funny part about uncertainty. The funny part about uncertainty is we can typically go 1 digit beyond the last, well, we can always go 1 digit beyond the last space, or the last marking. Depending on how big those markings are, sometimes we can do a bit of an estimation, sometimes we can't. If you look at those centigram balances, and you spent a lot of time looking at them the other day, I said you can really only estimate a 0 or a 0.5. It's either halfway between or it's dead on. Because the space between those things is so tiny, you know, unless you have caliper eyeballs, I dare you to try to say, no, that's really 0.6, not 0.5. Baloney. I don't buy it. This is a much larger instrument. The marking, or lack thereof, is a whole meter apart. We can probably, with some degree of reliability, say, yeah, I think that's 0.9. So now I'm going to give you another stick, because I just can't get enough of handing sticks to chemistry students early in the morning. There you go. Make sure you're looking at the correct side. Don't say I never gave you anything. There you go, ladies. And there you go. And last but not least, there you go. So, looking at the side that has the SI units on it. Do not look at inches, do not look at inches, do not look at inches. Do not look at inches. We hate inches. We hate state inches. Now can you measure the widest part of your desk? Okay. Write down the number you get. And here, I'll make somebody else's desk star in this one. Okay, Okay, what kind of numbers are you getting now? Dustin, what do you have? 0.94. So here we said we were getting 0.9 meters was our measurement, based on the last markings and going 1 decimal place beyond that. Whoops. So here you're saying, let's ask the question first before we start recording stuff. What's the last marking on this? So we have meters, we have centimeters, we have millimeters. So we could mark, I'm just going to put zeros in here. We have centimeters, millimeters, and we could go 1 decimal beyond that. So, you want to give me your answer again? We can go 1 decimal beyond that using this because it goes, the last marking is in millimeters, so we can actually go beyond the millimeters to what? Anybody? You can discuss it at your lab groups. I'll tell you what, come up with a table answer. Come up with a table answer for the most precise measurement you can make with the actual marked meter stick. We have a set of 6 measurements. Now, I'm going to assume that these desks are all identical. They were manufactured in a factory somewhere in China where I'm sure they have very strict quality control procedures. And, you know, I think the desks are pretty identical. But is it a potential source of error that you actually measured 6 different desks? Yeah. If we really wanted to do this right, I would have you all measure the same desk again and again. But assuming that these desks are completely identical, are these numbers accurate, precise, neither, or both? So let's first talk about the precision of the numbers. Are these numbers precise? Who would say yes? I would too, honestly. I mean, I think those are fairly tightly grouped. We have no variation in the hundredths column. We have very little variation in the millimeters. Now, a word about that last column. That's your uncertainty digit. Who here is actually a robotically enhanced human being with caliper eyeballs? Okay, Matthew, come on, your secret's safe with us. You can tell us. Colin, robotically enhanced bionic engineer. Okay, that would be pretty cool. You should take physics next year. Okay, probably none of you are honestly robotically enhanced with caliper eyeballs. I'm guessing, just my guess. It doesn't show up in any of your school little medical chart things that I should know. So that's good. I'm going to say that it's probably pretty hard between 1 millimeter mark and another to say that it's 0.2 or 0.9 or 0.7. When the marks are that close together, we typically default to saying you can either say it's dead on or it's in between. And so we would typically say that this column, this uncertainty, is either a 0 or a 5 with very little in the middle. Okay? And on your centigram balances, when you're massing things, that's typically the rule we go with, because the marks are so close together that short of like laser robotic calipers, you can't distinguish between 0.2 and 0.5 or 0.7 and, you know. So we typically use there the 0 to 5 rule. Okay, I think these are pretty precise. Can we know how accurate it is? Can we determine its accuracy? Who thinks yes? Discuss it at your tables. Come to a table vote. Barring contacting the manufacturer and getting the dimensional information on the desks, we probably can't know what the true value is. Now, I will say, flipping the desks over and measuring from the bottom side, like one group did with their cylinders, that was you guys, right? I can't remember who did what. Okay. would probably increase our accuracy. Why? Because of those curves. Curves are tough to measure around with a straight measuring device. Those are things that you can do to increase your accuracy. But we don't really know. I would say you overall got pretty precise measurements. Now, how do we keep track of how precise the measurements that we obtained the first time are? When you measured the desk with the big green stick, did you get a number that was more or less precise than using the fully marked meter stick? Significantly less precise, yeah. I mean, we said, I don't know, it's like 0.9 meters. And actually, that's pretty good eyeballing. If you look at the actual, or at least what we suspect is close to the actual value numbers, that's pretty good eyeballing. But we know that it's a lot less precise than using the fully marked meter stick. We keep track of that using Sigfigs. Anytime you get a set of measurements handed to you, the first thing you're going to do is look at how many significant figures there are in those measurements. There are rules for this. There are rules for this. So we look at a set of measurements, we look at how many sig figs there are, and here's how we determine it. If it's not 0, it's significant. Yay, that's easy. If it is 0, it's a little weird, and we're going to practice this today. If it is a 0, and it is between two non-zero digits, it's significant. So, 4, 5, 7. How many sig figs? 3. 4, 0, 7. How many sig figs? How many sig figs? 3. That is a 0 between two non-zero numbers. It is always significant. And I'm going to use little red checks to denote that they are significant. 4 and 7 are automatically significant. That 0 is between two non-zeros. It's significant. So what we're saying when we get a set of measurements is, if it's significant, we know that it tells us something about the precision of the instrument used. It tells us that we used the actually marked meter stick versus the big green stick. It tells us that there is a level of precision to the instrument. Okay, so the number 50029, how many significant figures? Count them. 1, 2, 3, 4, all 5 of them. Those zeros are between non-zeros, therefore they are significant. Even if there's more than one 0, but they're all between non-zeros, they are all significant. Okay, that's rule 1. So we got that. Zeros that are in front of non-zeros aren't significant. This is the toughest rule, I think, to understand and to remember. And I'm actually going to shrink this a little bit. I think you all have this already, so you don't need it. Whoops. Okay, so if I have 0.02, how many significant figures are there? Just one. This 0 is a placeholder 0. It is not significant. It's just holding the place, and you have to be really careful about placeholder zeros. So if I have 0.0008, how many sig figs are there? 1, because that's not, that is. What if I have, let me move this, what if I have 0.00702? How many significant figures do I have? Hold up fingers. I got 3. Excellent. These 2 are not significant. This is, and therefore that is. Okay. That one's not too bad. Move that aside. Move that aside. Zeros at the end of the number, right of the decimal, I tend to say behind the decimal, are significant. Those are significant. They're telling you about the precision of the instrument used. So if we have 5.0, How many sig figs? You can just vote with your fingers. 2. Yeah. That is. Okay. What if I have 0.5070? How many sig figs? Vote with your fingers. 4? I see a few 4s. Why 4? We're invoking 2 different rules here. Okay, 5 and 7 are significant automatically. Well, that makes this significant. There's our 3. What about zeros at the end of the number behind the decimal? Yes. Zeros at the end of a number behind the decimal are significant, so that is significant. Let me make it even weirder. 0.008070. How many sig figs? 4. Yes. Not significant, not significant, yes, 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 yes. Okay. Now, the next one is just, okay, so we got that one. Zeros at the end of a number left of a decimal may or may not be. So zeros at the end of a number in front of the decimal. And the way we determine this is whether there's a decimal behind them. So if we write 300 versus 300, like that. One of these things has 1 sig fig and one has 3 sig figs. Which one has 1 sig fig? Well, and it's impossible to say, like 300, because they're both 300, but the top one, I knew what you meant. The top one has 1 sig fig. These are not significant. They're at the end of the decimal. They're just they're placeholder zeros, like those ones in front are. The one at the bottom, by putting that decimal there, we are saying that those are significant digits. Those are precise. Those are known. So what I'm going to have you start with is a practice sheet, and the whole first section is just figuring out how many sig figs are in a number, and then we'll move on in a little bit to talk about other stuff.